So students, now let's start our second topic, and that second topic is apparent depth. Okay. So in case of apparent depth, we have two cases. Okay. So the first case is when object is in denser medium. Okay, so both the cases are important, but this case is little bit more important than the second one. So what is this? When the object is in denser medium. Now to understand this case, let's draw a ray diagram. Okay, so let's see this diagram. Okay, so let's say there is a coin which is placed at the bottom. There is a coin which is placed at the bottom of this jar. Okay, so this is a coin, and right now this jar is empty. Now, because this jar is empty, when the observer or any person can see this coin, so that person will see this coin at its actual position. Now, positions are always taken, or all the distances should be taken from the interface. So let's say this is the interface. Now, you know very well from my first lecture that what is the interface. Interface is a surface which separates the two media. Okay, so here this is the interface. If I so right now this is empty. Now because it is empty, so whatever person or a observer will see, when observer or a person will see this object or the coin, he will see it at its actual position. So I'm writing here dr. So this dr is what? Dr is a real depth of this object. Okay, and I am just mentioning this point as O. So this O is a real depth or the real position of this object. Okay. Now let's fill this jar with the water. So when I fill this jar with the water like this, so what happens then? Is it appear on the same position, or it will appear at some other position? So let's draw a ray diagram to understand this concept. So let's see here. So if I draw a ray, okay, if I draw a ray like this from this object. So now in this case, this is the normal incidence. Okay. So we just studied in previous lecture. In case of a normal incidence, the angle of incidence is zero and the angle of refraction is also zero. So this light ray will go straight like this. Okay. So this is the point. Now second, let's say that there is another ray and which is coming from this object like this here, and this is a point of incidence. In this case, let's draw a normal here. So this is a normal. Okay, this is a normal, and let's say this point is A. This point is A. So this angle is called angle of incidence. So this is the angle of incidence. Okay, now what happening? This water is my denser medium. It is our denser medium. So let's say that the refractive index of denser medium is mu d, and the outside medium is ray red medium. So refractive index of ray red medium is mu r. Okay, understand? This medium is denser medium. So refractive index of this denser medium is mu d, and refractive index of this ray red medium is mu r. So this is the light ray. It comes and incident at this point A. Okay. Now what is happening? This light ray is going from denser medium to rarer medium. So as we studied earlier, when the light ray travels from denser medium to rarer medium, it goes away from the normal. Okay. So the refracted ray. Okay. So the refracted ray goes away from the normal like this. This. This is the refracted ray. It goes away from the normal like this. Okay. And this angle is called angle of refraction. Okay, and this is the refracted ray. Now if my observer is here, so what happens, the image of this object will form, and when the image is formed when the refracted rays are actually meet or appears to meet. So you can see here I have two refracted rays. This one is my first refracted ray and this one is my second refracted ray. If it keeps on moving like this, it keeps on moving like this, so they will not actually meet somewhere here. Okay, so what we'll do, just extend this refracted ray in a backward direction like this, so it appears to cut at this point. And where it appears to cut, like if you extend it in a backward direction like this and this one, so both these refracted rays appears to cut each other at this point O dash, and O dash is an image of this object O. So when this observer will see that object, so he will see the image of that object, and this O dash is the image of that object. If there is a coin, so he will not see the coin at its actual position, he will see the object at its apparent position. This is the apparent position. Okay, so this distance, this from interface, this is called apparent position. DA is called apparent position. Okay, now what happens, it shifts normally from O to O dash, so this is called normal shift X. So in your examination these kind of questions comes, and they will ask you about what is the apparent depth, what is the normal shift. So let's derive the formula for the apparent depth and normal shift. Okay, so I hope you understand where the point, where the object, where the observer will see the object, he will see the object at its apparent position. And one more important thing you can observe from here, that if the object is in denser medium, then it will shift towards the interface. Okay, you can see that it shifts from O to O dash. Okay, so it shifts towards the, not it actually shifts, its image, obviously its image forms at this O dash. So it, we can say that apparently that it shifts towards the interface. Now let's derive a formula for the apparent depth and the normal shift. Okay, so I can apply the Snell's law here. So by Snell's law, okay, so what is happening here, my light ray is traveling from medium D to medium R. Okay, and you can see here, I just explained all those things. Here the light ray is traveling from medium 1 to medium 2. So what we write, mu 2 1, and mu 2 1 is equal to mu 2 by mu 1. Okay, one more thing you can mention here, that mu 2 1 is equal to what, mu 2 by mu 1. Okay, you can very easily derive this relation also. Okay, so this mu 2 1 is equal to mu 2 by mu 1. How it comes, we know that mu 1 is equal to what, C by V1, and mu 2 is equal to what, C divided by V2. Okay, so if I write from here, V1 is equal to, so V1 is equal to C divided by mu 1. Okay, and what is V2? So V2 is equal to C divided by mu 2. Okay, now mu 2 1 is equal to what, V1 upon V2. So when you write V1 is what, C divided by mu 1, and V2 is what, C divided by mu 2. C to C cancel, so we'll get mu 2 by mu 1. So this is a relation. So when the light rays travel from 1 to 2, I can write mu 2 1 is equal to mu 2 by mu 1. Now apply the same concept here. Here the light ray is traveling from D to R, so I can write the refractive index mu, refractive index of rarer medium with respect to denser medium, and it will be equal to what, mu R divided by mu D. Okay, and it will be equal to sin I by sin R divided by sin I by sin R. So I get this relation. I hope you understand this. Okay, mu R D is equal to mu R by mu D is equal to sin I by sin R. Now see from this ray diagram, this angle is I, so this angle is also I, and this angle is R, so this angle is also R. Let's say this is the point B. Okay, so now in triangle, You can see this triangle AOB. In triangle AOB, okay. So in triangle AOB, I can write as tan I. Okay, so this tan I is perpendicular by base. So perpendicular is what? AB. Okay, and base is what? This OB. Okay, and this OB is what? AB, and divided OB is a real depth, so I can write DR here. Okay, now in triangle AO dash B, AO dash B. So you can see that AO dash B, the tan R, I can write tan R is equal to again perpendicular by base. So perpendicular is what? AB. Okay, perpendicular is what? AB, and base is O dash B. Okay, now this O dash B is what? AB divided by O dash B is a apparent depth, so I can write DA. Okay, so understand this, tan I is equal to AB divided by DR, and this AB divided by DA. Now let's say these angles are very small, so I can apply the um, the concept of approximation. Okay, so angle approximation means if I and R is very small angle, so they are very small angle. So if they are very small angle, then I can write that sine I, or I can say that tan I is approximately equal to sine I, and it will be equal to what? AB divided by DR. Okay, now here tan R. So this tan R I can say approximately equal to sine R, and it will be equal to AB divided by DA. So I did here uh, angle approximation, and considering that I and R are the very small angles. Okay, now from equation 1, from equation 1. So from equation 1, I have mu R divided by mu D is equal to sine I. So what is sine I? AB divided by DR. Okay, and what is sine R? So sine R is AB divided by DA. So cancel out this AB to AB. You will get DA divided by DR. Okay. So from here, I want to know the relationship for apparent depth. So I can write that apparent depth is equal to DR and mu R divided by mu D. So this is the first relation we get for the apparent depth. Okay, for the apparent depth. So what is the formula? The formula is dA. dA is what? Apparent depth. Apparent depth is equal to real depth, and mu R by mu D. Okay, now when the question comes in your exam, so refractive indexes, mostly the refractive index of both the mediums will be given in a question, and the real depth is also given. You just apply this formula, you will get the apparent depth, and just remember the thing that all these depths are taken from the interface. Okay, now let's see what is the formula for the normal shift. So normal shift, you can see here x is a normal shift. Okay, so this x is equal to what? Dr minus dA. Okay, so let's derive the formula for the normal shift. So normal shift is x is equal to dr minus dA. Okay, so x is equal to dr minus dA. dA is what? dr into mu r divided by mu d. Okay, तो यहाँ से from here, okay, from here I can write that dr 1 minus mu r divided by mu d. Okay, so this is the formula for normal shift. Okay, and when we apply this formula, when the object is placed in a denser medium. Okay, so these are the two formulas. This is the formula for apparent depth. Okay, and this is the formula for normal shift in case when the object is placed in a denser medium. Okay, now let's move forward. I hope you understand. In case if you have any doubt, you can ask. Okay, now let's move forward. to our next case from this topic. And next case is when object is in denser medium. Okay, so denser medium we have done. So next case is when object is in rarer medium. Okay, sorry. So let's see the case. B point. Second case when object is in rarer medium. Okay. Now to understand this case, let's draw a ray diagram. Okay. So let's see here. Again, let's say this is the interface. So this is the interface. Okay. So this medium is a denser medium. This is a denser medium, and refractive index of this denser medium is mu d. And above this is a rarer medium. Okay. This one is a rarer medium. Okay. And rarer medium. Okay, so refractive index for this rarer medium is mu r. Now, in this case, our object is placed at the object is placed where? Now, in this case, our object is placed in a rarer medium. Okay, so let's say this is object, and this object is again I am denoting by O. Now, the distance of this object from this interface is dr. So this dr is a real depth. What is this? This dr is a real depth of this object from interface. Okay, dr is a real depth of this object from interface. Okay, now let's say a light rays incident normally light rays incident normally from this object like this. So we know this case. In this case, I is equal to 0. So R is also equal to 0. So this light ray will go straight like this. So this is my first refracted ray. This is my first refracted ray. Now let's see here. A light ray is coming from object and incident at this point. Okay. Incident here at this point. Okay. So now here I can draw the normal like this. This is a normal. This is a normal at this point. Let's say this point is A. This point is A. So this is my incident ray, and the incident ray, the angle makes with the normal is called angle of incidence. So this is I. Now in this case, what is happening? The light ray is traveling from rarer medium to denser medium. So when the light ray travels from rarer medium to denser medium, we already studied in a lecture that when the light ray travels from rarer medium to denser medium, it bends towards the normal. Okay. So this light ray bends towards the normal like this. So bends like this, and there is my observer. So this is a observer. Okay, so this observer will see the image of this object. Okay, now we already know that when the image is formed when the refracted rays are actually meet or appears to meet. Now in this case also there is no chance that these rays will meet actually. So we just extend them in a backward direction like this, and this ray also in a backward direction like this. Okay, so they appears to meet at this point, and this is O dash. So image is formed at O dash. So now here you can say that in our previous case, the image is formed towards the normal, or I can say that the object is appears to shift towards the interface. Sorry, towards the interface. Okay. Now here you can see that the object appears to shifts away from the interface. Okay, shifts away from the interface. So this distance, this from this O dash to the interface is called apparent depth. So this is the apparent depth. Okay, so this object appears to shifts away from the interface when the object is placed in a rarer medium. Now this angle is R. This angle is R, angle of refraction. Now because this angle is R, okay, this angle is R, so this angle is also R, I can say. Okay, now let's derive the formula for the apparent depth. For this case, let's make this line, and let's say this point is B. Okay, so this point is A. Let's say this point is M, and here this point is N. Okay, so these distances AB is equal to OM and is equal to O dash N. Okay, all these distances are same. Okay, or equal. So now again apply the Snell's law. By Snell's law. Now in this case, what is happening that the light ray is traveling from rarer medium to denser medium. So I can write mu dr. Okay, and this mu dr will be equal to mu d divided by mu r, and this mu d divided by mu r will be equal to sin I divided by sin r. Okay, this is my first equation. Here the light ray is traveling from rarer medium to denser medium. So I can write if relative refractive index of denser medium with respect to rarer medium, mu dr is equal to mu d by mu r, and it is equal to sin I by sin r. Now again I am taking or considering that I and r are the very small angles. So in triangle, let's take this triangle O OAM. Okay, this triangle OAM. So in triangle OAM, because we have done the same process earlier, okay, so I can write this tan I. So tan I is equal to perpendicular by base. The perpendicular is OM, okay, and base. So you can see that what is the base? This AM. This AM is parallel to OB, okay. So OB, and OB is what? OB is a real depth dr, okay. And because it is a small angle, so I can write it as sin I is equal to OM divided by dr by the angle approximation. Okay, small angle approximation. Now in triangle, let's say this triangle O dash AN, O dash AN. So in O dash AN, I can write tan R. So this tan R is equal to perpendicular O dash N. Okay, perpendicular by base. So base is AN. Okay, now this O dash N, you can see this O dash N is equal to OM. Okay, so I can write here OM and divide by AN. So AN is what? AN is parallel to BO dash, and this is a apparent depth. So I can write here DA. Okay, and by the small angle approximation, I can say sin R is equal to OM divided by DA. So now I hope you understand. Okay, in case if you have doubt, you can ask. Okay, now let's put the values here in equation 1. So from equation 1, I can say that mu d divided by mu r. Okay, it will be equal to sin I by, it is equal to sin I by sin r, and sin I is equal to OM divided by dr into, and this one is OM and dA. So cancel out this OM to OM. So it will be equal to dA divided by dr. So what is the formula we get for the apparent depth in this case? So dA is equal to mu d divided by mu r. Okay, mu d divided by mu r into dr. So this is the formula for apparent depth when the object is placed in a rarer medium. Okay, now let's see for the normal shift x. So in this case here, this, what is a normal shift? This O to O dash, this x is a normal shift. So this x is equal to dA minus dr. Okay, you can see clearly from this diagram, this x is equal to dA minus dr. So x is equal to dA minus dr. So what is dA? dA is mu d divided by mu r into dr. Okay, and minus dr. So from here we can get x is equal to dr mu d divided by mu r minus 1. So this is the formula for normal shift when the object is placed in a rarer medium. Okay, so let's see again both the formula for both the cases. So here you have dA is equal to dr mu r by mu d, and in second case the formula is dA is equal to mu d by mu r into dr. Okay, so and normal shift in this case when the object is in rarer medium is x is equal to dr mu d by mu r minus 1, and here formula is x is equal to dr 1 minus mu r by mu d. Okay, so you can see here again, this is the complete derivation for both the cases and for the apparent depth and normal shift. Okay.